All right, there we are. So, welcome everybody to Intro to Space Navigation, Spring 2025, Lecture 13. So I'm going to share my screen. So there we are. Great. So we're actually between two units right now. So I want to return to our course map and talk about that. Of everything we're going to talk about. We spent a while on orbital mechanics and kind of orbital mechanics related foundational things like attitude descriptions, or kind of a review of orbital mechanics, or orbit determination, orbit propagation, stuff like that. Once we finished up with that, then we moved into estimation theory, and kind of there was this one lecture on matrix vector calculus that didn't really fit into any of the units, but I guess that's kind of math, so we'll group it in here. And we've since gone through estimation theory. So we started with uncertainty quantification, was lecture 10. So we talked about covariance was the word of the day back then. Then lecture 11, we talked about kind of the three ever stronger solutions to a linear estimation problem. So there's least squares, weighted least squares, and maximum likelihood estimation. And then was on the batch estimation and the state transition matrix, also with the quick word observability. Your homework 2 is going to have one problem, batch estimation problem, and one problem that is a maximum likelihood estimation problem. And that's so today is lecture 13. So we're done with estimation theory. We're about to have a very short series on triangulation and trilateration. And then after that, we're going to have an extremely short series, just one lecture long, on inertial navigation, and then spring break. And then everything after spring break is the stuff that's really near and dear to my heart, which is star trackers, Kalman filtering, optical navigation, kind of the really snazzy stuff over here. But all of that is built on kind of the framework that we build up in the first half of the class. So today and tomorrow is going to be, as you can see in the diagram here, I kind of left it ambiguous. Are we using ground stations to track the spacecraft, or are we using the spacecraft to track ground stations? Are we measuring distance? Are we measuring line of sight? I kind of left that ambiguous in the diagram because the answer is yes. So over the course of the next couple of lectures, we're going to talk about space to ground navigation. So we know where the things in space are. We don't know where the things on the ground are. Think GPS. So all of us are GPS experts if we have a smartphone. And then there's also ground to space navigation. So we know where the ground station is. We don't know where the spacecraft is. An example of that would be the Deep Space Network, like when we're tracking things on their way out to Mars and so on and so forth. And then there's these kind of math problems, not exactly complementary math problems, but one of them is where you know ranges. So I'm here's a landmark, and I'm this far away from landmark A, I'm this far away from landmark B, and I'm this far away from landmark C. And if you have three lengths, that is trilateration. It's like you're finding there's three sides. So in that case, you're solving a trilateration problem, trying to find your position from range measurements. Ultimately, GPS is a trilateration problem. So we're going to have a trilateration homework assignment. And then triangulation is when you have line of sight vectors to three or more things, or in this case, two or more things should be sufficient. So, here's a point on the surface of the Earth, and I recognize, I guess, as drawn, one of those looks like it's in Madrid, Spain, and then the other one looks like it's, I don't know, somewhere in the United States. And you say, okay, well, look, I know where that point is in space, and I know the direction that it looks like it is away from me, and I know where this point is in space, and I know where the direction it looks like it is from me. So there's actually only one point in 3D space that lies on the intersection of those two lines, and that is triangulation. So if you're measuring angles, triangulation. If you're measuring lengths, trilateration. And that's going to be the topic of the next two lectures. So I want to make that make sense. And then also, this is homework 3. Homework 3 is going to have one triangulation problem, one trilateration problem. So questions on that before we get into the material today? So far, so good. Okay, cool. Let's start writing stuff down. The first half of the lecture today is going to largely be vibes. We're not going to get into math until towards the end of things today. So lecture 13 is radiometric navigation. Radiometric as in measuring radio signals. Or as I like to put it, how do we actually use those big ol' radar antennae? ENNAE. There we go. Never spell that word. How do we actually use those big old radar antennae? So maybe you're familiar, and this is going to be my kind of best depiction of a radar antenna. So you've got this kind of dish, and maybe it's got like some structure, and then there's like some bit at the end. And you might be familiar that we have these dishes over the surface of the Earth placed strategically to measure spacecraft that are on their way out into deep space. And we're going to talk about that in a moment. So I kind of discussed this in the kind of prologue, but if you have, I'm just going to say enough distances, then we are faced with a trilateration problem. You might say, geez, Paul, the tri prefix in trilateration makes me think that enough distances is 3 distances. And yeah, you'd think so, but no, that's not how that works. And then similarly, if you have enough line of sight directions, then this is a triangulation problem. We're going to go into gory detail on both of those next lecture. Today is going to be an introduction to this whole field of navigation, and then we'll set up some equations and we'll solve them next time. You might say, gee, Paul, the tri prefix in triangulation makes me think that 3 angles should be enough. No, that's not really how that works either. You actually need 2 line of sight directions or 4 distances to solve these, which is confusing. We're going to make this make a little bit more sense later, but that's the basic idea here. Now, I'll also mention, we haven't really talked about DSN yet, but I will say that there is something called DSN, which is a navigation system, and this gives us what is often referred to as R3B, which is really RRRB. Right? If you're using these radar dishes, when we're measuring a spacecraft, we can get range, we can get range rate, think Doppler, and we can get bearing or direction. So we can get a distance, a velocity component along that distance, and a line of sight direction from these radar antennae. We cannot get tangential velocity. So we're actually only directly measuring 4 out of the 6 states, right? So we're getting range and bearing gives you x, y, z, right? Like polar to Cartesian coordinates. And then range rate gives you 1 component of velocity, but we're missing the other 2. And what we'll find, and now we're getting way ahead of ourselves, is that a sufficient time history of range rate, and bearing is enough to reconstruct your entire state. It gives you observability over the other velocity components if you get enough measurements over time. Now that's homework 5, so we're like way ahead of ourselves on that. But just wanted to let us know these radar dishes give us these types of measurements. So some definitions. Radiometric nav systems use the principles of light propagation to infer information about the vehicle state. These systems use radio waves. So really quick, for anybody who knows, why do we use radio waves to navigate our spacecraft? Why is this radiometric navigation? Why isn't it, I don't know, UV metric navigation? Why are we using this specific range of frequencies spectrum? Yes, Peter.
Is it because radio waves are, for the most part, unaffected by Earth's atmosphere?
Exactly. Yep. Very good. Maybe you've seen graphs where it's like wavelength on the x-axis, and then like I don't remember how we would characterize it, but like the amount of that like wavelength that makes it to the ground through Earth's atmosphere. And you can see that there's like all manner of attenuation at different frequencies, and then radio waves basically make it straight to the ground. Sorry, this is kind of a poor visual aid here, but basically radio waves are largely unaffected by Earth's atmosphere. So we can send them up and send them down just fine. Now, they're largely unaffected. They are still affected, and we actually do need to take that into account. But for example, like, other types of radiation are blocked pretty effectively by the atmosphere, which is great, because if we didn't have things like blocking cosmic rays, we would all die. But it makes it difficult to use for navigation. So radio waves are in this nice sweet spot. Let's see. The spectrum of radar frequencies, or radio frequencies, I'll say. Frequencies. Has been divided into bands. Sorry, I just saw a word about hypersonics and I got curious. Let me read that. What's the chat saying? Think of change in the future. Hypersonic cannot be detected. Hypersonic speeds absorb radio waves. Yeah, it's a good point. So I think that for as we get to the point of frequently seeing hypersonic travel through the atmosphere, that could cause other issues. And then for that matter, during the reentry of a spacecraft, there's this kind of plasma shell that forms around the spacecraft. That's just the hot gases in the plasma that's being heated up by reentry. That creates this kind of envelope that basically we can't communicate through. So you can't send signals back to the ground through the plasma of reentry. Asterisk. So we're actually making some progress on that. But I'm looking forward to what new methods of navigation come out in the future in response to our kind of improved aerospace engineering. But for now, radio navigation is still the king. As much as I'm really giddy for autonomous navigation and camera-based navigation, which we'll talk about later in this class, those are backups on every spacecraft that I'm aware of. And then just track it from the ground is plan A pretty much every time. So the spectrum of radar frequencies has been divided into bands. Bands, that was the word I missed. The IEEE radar or radio frequency standard. I have a nasty habit of using radar and radio interchangeably, and that's not correct. Is okay. High frequency, or HF, is 3 to 30 megahertz. And the next band is very high frequency, which is, you'll notice that we're already starting off at high frequency and we're only going up from here. So there's no like a low frequency band. 30 to 300 megahertz. And then there is ultra high frequency, which is 300 megahertz to 1 gigahertz. And then there is L band, which is used by GPS. And this is 1 to 2 gigahertz. After that is S band, which is used by the Tracking and Data Relay Satellite System, or TDRS, which should sound familiar to everybody who's completed homework 1, which is basically the series of geostationary, or I guess not quite geostationary, some of them are geocentric or geosynchronous, but these are satellites whose orbital period is roughly 24 hours, that are, they roughly speaking don't move in the sky from an observer on the surface of the Earth. And we use these for communication. For example, with the ISS goes through TDRS. This is kind of the one of the de facto in-space communication methods that we've been using. So TDRS operates at 2 to 4 gigahertz. Right. The next is C-band, which is 4 to 8 gigahertz. And I'm going to scroll down here a little bit. Then we have X-band communication, which is used by the Deep Space Network, tracking new horizons and tracking, things that are crazy far away. Things like Voyager. We're still in communication with Voyager, to the best of my knowledge. So this is 8 to 12 gigahertz. Then we have, let's see, X-band. We have Ku-band. So Ku-band is 12 to 18 gigahertz. And K-band is 18 to 27 gigahertz. We have Ka band, which is also DSN. So DSN has kind of claimed both of these bands. 27 to 40 gigahertz. Let's. Next we have V band, which is 40 to 75 gigahertz. And W band, which is 75 to 110 gigahertz. Chiefly, we'll be working with GPS and DSN for this unit. But just for your awareness, these are the IEEE radio frequency standards. There are 2 fundamental classes of radio frequency, or we'll just say radio wave measurements. There is time-based, which uses signal time of flight to estimate range. And there is frequency-based. Which uses Doppler frequency shift to estimate range rate or radial velocity. All right, so let's start talking about those. First, I want to talk about time of flight or time of arrival measurements. Let's see, yes, Peter.
I might be misreading it because I'm just still writing out all the bands. Did you write Ka band twice?
That's KU.
Oh, my bad. Sorry.
Can't you tell? No, I'm just kidding. My handwriting is, there you go. Perfect. Thank you for keeping me honest. So then first method I want to talk about is either time of flight, or sometimes you'll hear it called time of arrival. TOA. So this one is maybe the one that we think of first, which is, okay, if we start a stopwatch and we send a signal, and then we stop the stopwatch when we receive the signal, and then we take into account the speed of light, then the length of time that the signal was floating through the air is related to the distance of me from the sender, so the sender-receiver distance, right? And so that is this. We can estimate distance between transmitter and receiver by measuring the light time between them. So if you estimate positions, so estimating position using only range measurements is called trilateration. This is fundamentally how GPS works. Now, my question for you, and I'll draw a little picture here. How many measurements do you need to get a solution? I guess I kind of alluded to this earlier, for a time of flight or kind of a range-based approach to estimating your position. How many measurements for a 3D position? Yes, Christy.
Is it 3?
It is 3 in 2 dimensions. And I'm going to draw a picture and make this make a little bit more sense here. So let's say you've got some point, and actually, I don't know how good of a job I've done here. Let's see. You know what? I might try something new on the fly here. Stand by, Christy. Let me try to draw a shape. It's going to work. Let's try that. I'm about to need to draw a bunch of shapes, so we're going to see how well this goes. And then, can I just like copy paste this shape? Oh yeah, now we're talking. Okay, so let's say for a moment that you know that you are some distance away from some point right here, and you are some distance away from some point right here. Then you might say, okay, in 2 dimensions, if we're in 2D space, then 2 ranges ought to be enough to get a solution. And it is. If you know you're some distance away from point A and some distance away from point B, let's say you're at, let's call this distance R1, and then we'll call this distance R2. So you're at some radius R1 away from this point, and you're at some radius R2 away from this point. You'll see that there are, in fact, 2 solutions. Right? So you might say, well, Paul, you told me that as long as the number of pieces of information is equal to the number of degrees of freedom in the problem, then you're good to go. And this is a 2-degree of freedom problem, and you get 2 ranges, you should be good. And it's like, yeah, well, real life sometimes doesn't treat us that well. And you end up with these ambiguity problems. So really, 2 ranges is enough to get you almost all the way to a solution, but you'll need a 3rd one just to be absolutely sure. So then we'll say, okay, let's say you're also at some range R3 from some 3rd point, and now all of a sudden it's obvious which of the 2 solutions it is. Right? So it has to be right here. So to go back to your point then, Christy, in 2D, we need 3 ranges. So in 3D, how many do we need?
4?
4. And we will later go through and set up a system of equations and show that you need 4 ranges to actually solve the equations to deal with this ambiguity problem. Okay, great. Thank you very much for everyone's participation. So that is time of flight. Next is, there we go. Next is time difference of arrival, or TDOA. So in this case, we are using the difference between time of arrivals, as the name would imply. So using the difference between, I guess it should be times of arrival. Times of arrival of signals from different stations to estimate position. This is sometimes called hyperbolic positioning. Since the stations, or I'll say since pairs of stations generate hyperbolic position surfaces. This is used by some pilots requires solving intersection of hyperbolas. And you need 3 or generally 4 stations. For a 3D position. So unfortunately, I'm going to have to free draw this one, but imagine you've got some signal over here, and then you've also got some source over here. You can just imagine that, over here, you're at some point where, well, here. Anywhere along this line would measure the same time of flight from the signal from over here to a signal over here. So if you're at this point, you're the same distance away. If you're at this point, you're the same distance away. Then there's going to be these hyperbolas, which each of these dotted lines are kind of lines of constant, like any point on this line would explain that signal, if that makes some sense. And so then what will happen is, so these are lines of constant position. So let's say you, anywhere on this particular hyperbola, will receive the same time difference of arrival from station A and station B. But then let's say you also have station C, you'll find yourself on a different hyperbola, and ultimately you're solving for intersections of hyperbolas. Whereas here with time of flight, you're solving for intersections of circles, basically the idea. Okay, the next one I want you to know about is called very large baseline interferometry, which is just a whole mouthful. Very large baseline interferometry, or VLBI. This is one that when I'm doing research, I keep seeing VLBI mentioned. I'm just like, oh, cool, there it is again. The idea here is, you can just kind of think about it for a second, it's interferometry with a very large baseline, as the name would imply. Very large baseline, like a substantial fraction of the surface of the Earth. Like we're going to go work together with our friends in England or something like that to determine well, we'll see in a second here. So we're comparing same signal from a distant object as received by 2 stations, I guess 2 or more, separated by a very large baseline. I'm going to try that again. And ultimately, we're not after distance, we're trying to determine direction. This is typically done with stations separated by a significant fraction of the surface of the Earth. And we ultimately determine direction from time difference. So hopefully this picture will make some sense here. I'm going to draw the Earth. You know what? I'm going to start making more and more liberal use of this shape feature because this draws circles so much better than I can. There we go. Here's the Earth. Here is one station. And then here is another ground station. And let's say there's some point source out here, and it's transmitting radio waves. And so you can imagine that each wave front, as you get further and further away from the source, is going to start to spread out. But the effect is that the wave fronts are almost, and as a matter of fact, I'm going to draw it such that by the time you get to the Earth, they're basically parallel wavefronts. You're so far away that you're getting parallel wavefronts. And you'll see that this station is going to receive its wavefront sooner than this station receives its wavefront. So this is going to receive at some time t1. This is going to receive at some time t2. This is what's called a collimated signal. So the original radio source is so far away that by the time the signal makes it to Earth, it might as well be parallel radio waves. It might as well be infinitely far away. But we say, oh, okay, this station receives sooner than this station. Based on that delta t, we can estimate the direction, that sort of thing. So that's all I'll say about that. We're not going to spend a lot of time on VLBI or time difference of arrival. I want you to be aware of them, but we are going to go into detail on this time of flight guy. So that's coming up. So this is a natural pause and catch our breath moment. Any questions on anything we talked about so far? Nope. Okay, cool. So we're going to talk about an example RF system. RF as in radio frequency, which you might have heard of, GPS. So the United States Global Positioning System, which I'm going to take a minute, maybe after I fill this in, to kind of sing the praises of GPS for a moment. GPS is one example of a number of global navigation satellite systems, or GNSS. So if you're doing your research and you read about GNSS, it's not necessarily the same thing as GPS, it's more general. You could think of GNSS as like a tissue and then GPS as like a Kleenex, right? Although Kleenex has become like a non-proper noun because it's used so frequently, but it's not just GPS. So it's also worth mentioning that Russia has their own thing, which is called GLONASS. And the European Union has Galileo. cool name. And China has something called Beidou. So same basic idea. And I just want to sing the praises of GPS for a moment, because it's not until you really sit down and study navigation. It's like there are so many cool tricks that we have to determine the position and I guess also the velocity. But for now, we're talking about position. There's so many cool tricks we have to determine your position in space. There's so many cool tricks on the surface of the Earth. You imagine you're lost on a boat on the high seas, but you have a nautical sextant. You can determine your position that way. There's star-based navigation. There's all sorts of fancy stuff you can do. But for all practical purposes on the Earth, navigation is a solved problem. Like it's unbelievable how well we've solved navigation. It's incredible. It's like as long as you have a GPS receiver, you know where you are anywhere on the surface of the Earth. It's like, man, we have dominated this problem, which has been something that has confused and stumped people for like all of human history. Just think about, traveling across the Earth, exploring the high seas, that sort of thing, going to the New World, and getting lost along the way. Like we don't do that anymore. You know where you are on the surface of the Earth, and GPS works in space for low Earth orbits. And there's even some work on R&D for using GPS higher up. It gets a little complicated. GPS really is built to work on the surface of the Earth, but it's kind of one of those like you kids don't know how good you have it moments where it's like GPS has solved navigation, which is just stunning. We could go on and on about how cool that is. I remember I was talking to I met somebody who was a navigator for the Merchant Marines, and I was asking her like, "Oh, you're a ship's navigator? That's so cool. Did you learn how to use a sextant?" And she's like, "Yeah, I mean, we had one, but we just used GPS." And I was like, "Oh, okay. How did you determine your velocity?" Like I heard that knots is like an old nautical term where they would actually like drop a rope out of the back of the boat and then, count the number of knots that the water pulled off the deck, and then that would be your speed in knots. And she's like, "No, we just did GPS and then did GPS a second time and then took the derivative. And there's our velocity." And I'm like, "Dang, so you're just a GPS machine, huh?" It's like I wasn't quite that rude about it, but it's like yeah. Anyway, I digress. GPS is really cool. We're going to talk about how it. So there's going to be a homework problem on GPS. So GPS performs navigation by trilateration. And we'll see two ways to solve that math problem next class. And consists of 3 segments. Okay. So the first is the space segment, which is the part we think about, the bit that's in space. But this is only the tip of the iceberg. So there are 24 satellites in the baseline configuration. There are more now. The satellites are in near circular 12-hour orbits. They have a 55-degree inclination. And so you can imagine that there's this GPS swarm. As a matter of fact, I might see about drawing a picture here. Let's do the Earth trick again. Yep. So you can imagine that each one of these is in an orbit which is like that. So roughly 51 degrees inclined. And so because of that, you're going to get fantastic coverage between 55 south and 55 north latitude, but you're going to start to struggle up near the poles. So GPS will struggle near the poles. just because of a lack of coverage. Actually, I saw a YouTube video one time of somebody who was flying. Their flight went basically over the North Pole. And as they went, they had the GPS on their phone, and it just started freaking out. It didn't know where they were. So I guess maybe I spoke too soon when I said that navigation is a solved problem. It's a solved problem for most populated areas of the Earth, but it does still struggle near the poles. And the 12-hour orbital period, yes. Oh, I thought that was a raised hand. That's a lowered hand. If anybody has a question and I don't see your raised hand, you can just call out.
I was just going to comment that if I recall correctly, that's why the Russians built GLONASS to be in Molniya orbits. They actually spend most of their time over the poles, so that they could use it in Siberia.
Ah, very cool. That makes a lot of sense. Be complementary to what we already have. There's also 6 fully spaced planes with 4 satellites each. Do this. There we go. So I'm going to struggle to draw 6 of these, but you can imagine that here's the first one, but then there's also another orbit which kind of goes more like this. And there's another one that maybe comes down in the middle like this. I don't know if I'm doing the best job of this, but you get the idea. And then we'll have another one that looks like this. And so each of these is roughly 51 degrees inclined, and you have them spaced out such that basically you should always be able to look up and see a certain number of these satellites. And that would give you enough for your position fix. So the next is the control segment. This is the space segment. There's the control segment. Having 24 satellites is not enough to solve navigation across the surface of the Earth. There is a master control station, which is near Colorado Springs. Which operates the satellites. There is a constant need for precise orbit determination. We have to know exactly where every spacecraft is at all times. There are literally dedicated supercomputers to this. We can't just let these things drift. There's also a global navigation, or sorry, global distribution. I got excited. There we go. Global distribution of Space Force monitoring stations. So the idea then is you've got these Space Force monitoring stations. We track the spacecraft. We determine exactly where they are with a great degree of precision. And that gives us part of the puzzle. So as we'll see the math problem set up later, you need to know your distance away from something that you have a great deal of knowledge where it is. That's the idea. So you need the position of your beacon point, and you need your range from the beacon point. But without a really high accuracy position for these satellites, we're not going to have a very high accuracy solution on the ground. And then there is the user segment. It's like at the end of a PBS thing where it's like, and viewers like you, thank you. It's like, well, yeah, so your phone or your GPS receiver does some of the work as well. So static and mobile GPS receivers that process GPS signals and solve the trilateration problem. And this includes your phone. All right. So this is one way of processing things. Now imagine we go back up to our little diagram here, that you've got a, I'll scooch this over here. Imagine that you've got, this is the center of the Earth. There we go. And imagine that there is a person like you who is at some position R from the center of the Earth. And now imagine that there is some spacecraft up here, and you can measure your range from it. And then there's some other spacecraft over here, and you can measure your range to it. And then there's some other spacecraft all the way over here, and you can measure your range to it. Right? That's kind of the idea here. So by getting 3 ranges to 3 things that are known very well, or sorry, what am I thinking? 4. So you can also measure this one here. So by getting 4 distances from 4 known points, that kind of gives you your position. And then also, you can think of it this way. The amount that you don't know where your spacecraft is will cascade into where you don't know where you are, right? So if you're saying, well, I know where I am because I trust these spacecraft positions, you see the importance of really getting this precise orbit determination problem down pat. All right, on to the next thing. So the next is another example RF system. And that is the Deep Space Network, or DSN. Christy, I see your hand up. Is that a stale hand up, or are you waiting for me?
Oh no, I think it was stale, but thank you.
Okay, no problem. Deep Space Network, or DSN, is the most scientific, or sorry, the most, getting ahead of myself, sensitive scientific telecommunication system in the world. Or out of the world. Unless we find out that there's aliens with something cooler. This is as good as it gets. This is operated for NASA by Caltech's Jet Propulsion Laboratory, or JPL. Established in 1958. This is the primary means of communication and radio frequency navigation with interplanetary spacecraft. So pretty much everything JPL does, when you think of like the Mars rovers, or you think of like the New Horizons mission, that's Deep Space Network. Also, like when we send people back to the moon for the Artemis missions, that's also Deep Space Network. So if it's anything beyond low Earth orbit, generally Deep Space Network. That's the way to do it. So the DSN consists of 3 deep space communications I just can't write today. Complexes. These are going to sound super arbitrary, but bear with me here. One of these is in Goldstone, California. So think Mojave Desert. Another one is in Madrid, Spain. And the third one is in Canberra, Australia. So why those three? They seem completely arbitrary. Anybody have any guesses? Yeah.
I'm guessing they're probably, give or take, equally distributed on the Earth's surface.
Yeah. Now, I guess there's probably other solutions to that problem, but also like we're friends with Spain and we're friends with Australia, and these are not like war-torn areas. But roughly, yep. If you've got one station that is here, actually, you know what? I'm going to color code this, and this is about to look really cool. Hang on. Let's say there's a blue station right here. This blue station can see almost 180 degrees of unobstructed sky. Right? And then let's say that there is a red station that is 180 degrees over this way. And it can also see almost 180 degrees of unobstructed sky. And then let's say that there's a green station over here, which can itself see almost 180 degrees of unobstructed sky. Then what you'll see is these are basically 120 degrees apart. And so you'll get these blind spots here. Which are close to the Earth. But once you get out beyond those blind spots, you basically have full uninterrupted coverage of space. So there's continuous coverage of deep space. So wherever Mars is, it's not in one of these blind spots. Each complex has several antennae. So we've got an 11-meter dish, one of those. You've got a 26-meter dish, one of those. You've got several 34-meter dishes, and then one 70-meter dish. These are diameters. 70-meter dish. So approaching the size of a football field. This is an absolutely massive station. Right? Now, some of you might have heard, and this is probably old news by now, that I think it was the Australia 70-meter dish was down for a couple of months for renovations or for repairs. And during that time, we lost communication with Voyager until it came back up again, which like people were upset. They're like, well, we want to hear from Voyager, where'd it go? And so I'm curious what your thoughts are on this. Why, if we just lost a single dish, did we lose communication with a spacecraft? Doesn't the Earth rotate? Like, won't one of the other dishes get it eventually? Or won't it orbit into a position where it will find itself in another? Basically, the Canberra, Australia is the only southern hemisphere coverage that we're getting, right? So Madrid, Spain, and the Mojave Desert, those are both in the northern hemisphere. And remember that Voyager is not orbiting, it's just spiraling off at this point. So it's now far enough away from the Earth that it does not appear to be moving generally. It's pretty much just getting smaller. And so it's not, I mean, it is on a conic section trajectory, but it's pretty darn close to rectilinear at this point. And yeah, it's in a position where we had a permanent blind spot of that part of the sky until that station came back online. So finally, I'll mention that there is a centralized signal processing center which is at JPL, which remotely controls the 34-meter and 70-meter dishes. It generates and sends spacecraft commands, and it receives and processes spacecraft telemetry. Modern spacecraft communicate with the Deep Space Network on X-band and Ka-band. And we mentioned before that DSN uses range or produces range and Doppler measurements. But there's also something called delta DOR, which is delta differential one-way ranging. Which is a form of VLBI. Remember, very large baseline interferometry. So the fundamental RF measurements are range and Doppler. But then if you're also getting this difference in time of arrival, you can estimate your, in this case, it would be direction. And so from those three, we get range rate, and bearing, or R3B. And want to do a quick diagram, and then we'll cool it for now. We'll take a little break. So draw some circles here for the Earth. Yep. So the kind of simplest way of doing this is one-way ranging, which works near Earth. And so the idea here is you've got your station and you've got your spacecraft. And in this case, you're basically just blasting out, well, here's what time I think it is. And then you get a measurement and you say, well, wait a minute, now my clock and this clock are different. They're different because of this time of flight. Now there's other effects that will affect that. But generally you're saying, okay, I'm just blasting out a signal. It goes to the DSN. You get this one-way ranging. And with this, there is no way to remove clock bias. The fact that your clock and my clock, not only do they disagree because of light time of flight, but also just your clock will slowly be wrong over time. So you've got this clock bias. This is near Earth. Generally, we do two-way ranging. Especially for like Jupiter and beyond. And in this case, we've got our ground station, and we will send a signal up to the spacecraft, and then the spacecraft will send a signal back down to the Earth. So we're actually getting two measurements, right? Assuming there is some calibrated turnaround time. And we're measuring the time that it takes to go out and the time that it takes to go back. So the spacecraft echoes signal, and this can remove clock bias. And we'll talk plenty more about clock bias coming up. There's also three-way ranging. And so this would be like Pluto and beyond. And in this case, we would say, okay, let's say we've got one ground station here, and then another ground station that's here. Oh, I can do a bit better than that. There we go. And in this case, you've got your spacecraft, which is way out in the middle of nowhere. And rather than sending out the signal once and then waiting for it to come back, we have this once out, once back, and once over technique. And we simply do this because the signal takes hours or days. So we tend to prefer three-way ranging out beyond Pluto. Okay, sorry, I would have liked to have stopped for a break about 5 minutes ago, so we're a little bit behind schedule. But why don't we say, let's take a break, and we'll come back at 7:16. And after this, it's all math for the rest of the lecture. All right, welcome back. So I want to spend the rest of our time going through kind of a toy problem to warm up on trilateration. And then we'll go through and describe in a little bit greater detail the measurements that we'll be taking. So this is a trilateration toy problem. Okay, so imagine you've got some spacecraft at some position R, and you've got some ground station. Let's say you've got like a beacon, and this is at some position P. We'll call it the ith beacon, and you're measuring range. And you could just easily do it the other way. You could say the spacecraft is what we know where it is. We don't know where we are. That's fine. For now, we're going to say we know P and we don't know R. Kind of doesn't really matter whether what's in space or what's on the ground is the known or the unknown. So we know one scalar measurement of range equals one piece of information. We know position is 3 degrees of freedom, x, y, z. Therefore, 3 measurements gives a solution. Not exactly. 4 measurements gives a unique solution. I'm going to go through and show why. So let's define it's a unit vector, and this is the position of the unknown object. So R is what we're ultimately after. It's R minus pi over the norm of R minus pi. So it's the line of sight direction. You think of it that way. Okay. And then also, so this is by definition. And then also rho I is the range. So this is just R minus pi. Okay. So the challenge is this. I want to give everybody about 5 minutes to try their best. Build a linear set of equations to solve for R given many ranges. I'm not going to limit you to a certain number of ranges, but given this information, go ahead and set up a linear system to solve for R. And I'll give everybody about 5 minutes to try it. Okay, so I'm going to go through and show the method that I came up with. But I'm curious, was anybody able to get this to work? And if so, was it easy to find R, or did you have to use any weird tricks, or what was your experience?
I only managed to get as far as I'd probably need you need four measurements, but given you're solving for, you should be solving for three variables, shouldn't you? Need it's either three or four equations. I wrote down four. Well, I wrote down that I needed four. I didn't manage to get four down.
Yep, I think you definitely need 4 to solve this particular problem, which I will make a note, and we'll note this again at the end, that this is a toy problem. We're not considering clock bias, right? So in reality, this is just kind of like a warm-up exercise. The way I would do it is write out this equation such that you could go through and kind of expand, basically. So the norm of r minus pi is rho I. So what I'm going to do is square both sides so that I can write this out. Remember that the norm of r minus pi is really the square root of r minus pi transpose r minus pi. And then it would be the square root of this, but we've squared it, so we're to this point here. And if you've made it this far, then already we're kind of, okay, we're coasting to a solution at this point, right? Let's go through and distribute. R transpose R minus 2 pi transpose R plus pi transpose pi. And I'm actually going to also subtract rho I squared is equal to 0. Or actually, let's work it this way here. R transpose R is just the scalar R squared. Okay, here, this is negative 2 pi transpose R. And then pi transpose pi, that's just the scalar pi squared. It's the position scalar squared. So I'm going to rework this to, it's actually rho I squared minus pi squared, like so. And believe it or not, we're basically done at this point. So the way I'm going to rewrite this equation is to say 1 and negative 2 pi transpose multiplies some state vector. Here's the secret. We're not going to get around this r squared. So we're just going to estimate it. So it's kind of bumming us out. I don't really care about r squared, but we're not going to get away from estimating that. And then we have r here. So our state vector is going to be a 4 by 1 in this problem. Part of the reason I went through this, and then this is a 1 by 4, and this equals rho I squared minus pi squared, which is also a 1 by 1. And so now we have a situation where we've basically, if we stack 4 measurements, 4 or more measurements, we get something that looks like ax equals b, and then we can solve using least squares. In this case, we're assuming that the knowns are our positions, our measurements is the range, and what we want is r. And this r squared term is basically dead weight. We're not going to get away without measuring. And this is a way to solve the problem. I'm sure there's other ways, but I'm curious, does this look kind of like what someone got to, or did someone get to something completely different? I'll leave a note here too. This is a toy problem in which we ignore clock bias. So in reality, it's not this simple. So this warm-up exercise, if you made it, great. If you didn't make it, it's not the end of the world. Homework 2 has a problem that it kind of looks like this if you squint. So this way of like writing out the equation and then isolating the variable that we're after and setting up an ax equals b problem. Definitely, if this made no sense, let's talk about it, because this is going to be something that comes up again. But now that we've done a warm-up exercise, I want to show you the full, well, we won't be able to get through it today, but I want to go through and set up the measurement equation. And then later we'll talk about 2 ways of solving it next class. Sorry, we're going to run a little bit longer than I want to do here. Is radiometric ranging. So suppose we want to use flight, time of flight, to estimate distances between points in space. Okay, let's say we have the position of receiver, which is r as a function of t. We also have a propagation time, or time of flight, tau. Then we have position of transmitting antenna. Okay. So this would be r sub t for transmitter, but this is at t minus tau, right? Because you're not really measuring where the thing is right now, you're measuring where it was when it sent the signal, right? So this is at time the signal was sent. Okay. Biases in both clocks cause the measured time to differ from true time. So on your phone, you'll never really notice a clock bias because your phone is regularly checking against the internet to see what time it is. But the clock in your car will start to drift. I think a lot of you will notice that when you change the clock in your car for daylight savings, you often need to change it by an hour and a few minutes because over the course of 6 months or however many months, you've lost about or you've gained about 2 or 3 minutes generally. Now, maybe if your car also connects to the internet, this is a moot point, but mine's kind of old. It's got a regular old clock that's not plugged into anything. And so you can watch it kind of drift slowly over time. And you might say, dang, this is a pretty good clock if we're only losing a few minutes in 6 months. It's like, that's totally not good enough for GPS. You really can't have an incorrect clock when tiny, tiny fractions of a second matter, because that's ultimately what you're measuring. Then you really can't afford to have an unaccounted for clock bias. So you've got transmitter time, which is the time as seen at the transmitter, which is itself a function of time, tt of t. I promise it's never going to get this confusing again in this class. This is the true time plus some delta tt of t. And then there's receiver time, which is tr of t, which is some true time plus some delta t r of t. So you can think of this as bias. This is true. Okay. The difference between measured transmit and receive time is used to obtain the pseudo range. Why pseudo range? Well, because we're not directly measuring range, we're measuring pseudo range. Also, you'll see the difference in a second here. So range, which is a function of time, is the speed of light times the difference. So we have TR of t minus TT of t minus tau. Now, even then, this is the speed of light, which is not as simple as you think. So there's actually quite a bit of complexity that I'm going to leave out of this unit because I think it goes beyond the scope of this class. But the speed of light is constant in a vacuum, but it is absolutely not constant in the outer atmosphere, in the interplanetary medium, in the regular atmosphere. The speed of light is definitely going to change as we, do our navigation work. We humans live in the atmosphere, so we do have to take into account these atmospheric effects. But we're saying the difference between measured transmit and receive time multiplied by the speed of light would give us this range. Okay, let's go through and expand this a little bit. Rho of t is equal to c, and in parentheses, t plus delta t r of t minus t plus delta t of t, of t minus tau, and then minus tau. So all I'm doing is just substituting in, right, the transmitter time and the receiver time from above. And we can go through and simplify things a little bit. This t and this t will cancel out. We end up with this kind of delta t minus delta, well, you'll see in a second here. Rho t is equal to c, and then delta tr of t minus delta tt of t minus tau. And then this is minus minus, this is plus tau. Or you could think of it as being c tau, which is really what we tend to think. We say, okay, this is the true transmit time, and then there's also multiplied by the speed of light, there's your range. Okay, that's really what we're after. But then there's also this other annoying bit, which is c and delta tr of t minus delta tt of t minus tau. So this is what we're after, or we'll say the interesting bit. And then this is junk that's coming along for the ride. So this is a function of clock biases. Okay. Really, c tau is then itself equal to the range distance. So we've got rr of t minus rt of t, what we're actually after. And then there's all of these delays. So there's also a delay because of the interplanetary medium. There's a delay because of the ionosphere. There's a delay because of the troposphere. We're largely going to ignore these, but I want to mention troposphere delay, ionosphere delay, interplanetary medium, delay. And then this is what we're after. Okay. So therefore, our pseudo range measurement is, so we're still talking about true range here, so just continue to bear with me for a moment. True range, rho of t, is what we're really after, which is this distance. So we have RR of t minus RT of t. Or I guess in the diagram above, this would be R minus PI, right? Same concept, we're just changing our nomenclature a little bit. So this is what we're after, plus C, and then delta TR of t minus delta TT, t minus tau. But generally, we can say that this bit is calibrated. And then we've got these dumb delays coming along, right? So there's the fact that light is delayed by going through the interplanetary medium, by going through the ionosphere, by going through the troposphere. So this is the pseudo, say right here. In reality, we estimate these using complex models. In this class, we will ignore. Which is strictly cheating. You can't do that on a real GPS problem, but this is an introductory course. So our pseudo range, which has this little tilde on top, is going to be R sub t minus R t of t plus C delta t R of t. So we understand the transmitter bias. We've kind of calibrated that out, but there's the receiver bias. This would be like the bias on your phone's clock, that sort of thing, right? We're going to call this whole bit here B of t, and this is the receiver clock bias. Okay, so finally, say dropping of time for brevity, kind of writing of t, right? Then we have a problem that looks like this. Rho sub I tilde, our pseudo range measurement, is R minus, so this is RR minus RT, or I guess in the nomenclature of our toy problem, this would be R minus PI. This is the ith transmitter, plus B. Or you could think of this as RR minus RTI transpose RR minus RTI to the 1/2 power plus B. So now solve for RR, the receiver position, given many pseudo range measurements. Next class. Because that's we're doing a to be continued right now. Kind of ran out of time, but I think this is a good natural stopping point. So we'll discuss this in the future. But you can see we've set up for this type of math problem where rho I is this function of our transmitter position, which we assume we know, our receiver position, which we don't assume we know, that's what we're after. Then we've got this nagging bias term that we don't want to have to deal with. It's really annoying. And we want to show a couple of different methods of solving this. But for now, this is to be continued. And we will show how to solve for this next class. So apologies for keeping us so late. Hopefully next time it's a little bit smoother. But yeah, any questions? Otherwise, we can stop for now. Cool stuff. All right. Thanks, everybody. Class is dismissed. And I'll see you next time for lecture 14.